In this lesson, we're going to explore the chemistry of benzene, focusing on aromaticity and electrophilic aromatic substitution reactions. Benzene is an aromatic molecule, which means that it possesses aromaticity, a powerfully stabilizing form of resonance. In order for a compound to be considered aromatic, it must meet four specific structural criteria. First, the molecule must have a cyclic structure. Second, each atom in the ring must have an unhybridized p orbital, typically from sp2 hybridization. Third, all of the atoms in the ring must exist in the same plane. And because sp2 hybridization is trigonal planar, this is usually the case when all of the atoms in the ring are sp2 hybridized. And last, the ring must possess 4n plus 2 pi electrons. This is known as Huckel's rule, and the expression 4n plus 2 is used to generate numbers of pi electrons that enable a molecule to be aromatic. In this expression, n can be any non-negative integer, so 0, 1, 2, etc. In order to be considered aromatic, a molecule must have in its ring a number of pi electrons that can be generated from this expression. So, for example, applying a value of n equals 0 would give us 4 times 0 plus 2 equals 2. So a molecule that had 2 pi electrons in its ring would follow Huckel's rule. Plugging in n equals 1 would give us 4 times 1 is 4 plus 2 is 6. So a molecule that has 6 pi electrons in its ring again would follow Huckel's rule. The expression 4n plus 2 is actually a way of generating odd numbers of pairs of electrons. So for example, we were able to get 2 out of Huckel's rule by plugging in n equals 0, and 2 is an odd number of pairs, 1 pair. We were also able to get 6 out of Huckel's rule by plugging in n equals 1, and 6 is an odd number of pairs, it's 3 pairs. And so some people find it easier to think of Huckel's rule as simply having an odd number of pi electron pairs. So let's take a look at a few examples of molecules that exhibit aromaticity. In our first example, naturally, we have benzene, by far the most common aromatic system. We can see that benzene is cyclic and that each of the 6 carbon atoms in the ring are sp2 hybridized. There's nothing that disrupts planarity, so we can assume that all 6 of those atoms in the ring are in the same plane. And so that just leaves us to determine how many pi electrons are in that ring. Pi electrons are simply electrons that are involved in a pi bond. And we can see that benzene, having 3 double bonds, will have 3 pairs of pi electrons. And 3 pairs is an odd number of pairs. And so benzene follows Huckel's rule. And because it follows all of the other criterion for aromaticity, benzene is aromatic. Our next example is a little more complicated. Here we have the cyclopentadienyl anion, and I've drawn out 2 of the 5 possible resonance structures. We can see that the cyclopentadienyl anion is cyclic, and that 4 of those carbon atoms are clearly sp2 hybridized, but the carbon that is negatively charged and has a lone pair appears to be sp3. But if we apply our knowledge of resonance, we know that a lone pair adjacent to a pi bond is actually a part of the delocalized system, and will be involved in resonance. We can push that lone pair up towards the carbon to the left, creating a new pi bond, and breaking the existing pi bond on that carbon, depositing the electrons as a lone pair. If we look at this second resonance structure, we can see that that bottom carbon, that appeared to be sp3 in the original drawing, now appears to be sp2. And remember, in a resonance system, if an atom ever appears as sp2, it really is sp2. And that means that all 5 carbon atoms in the cyclopentadienyl anion are in fact sp2 hybridized. Because of this, we can assume that those 5 atoms can exist in the same plane, and so that just leaves the calculation for Huckel's rule. Looking at the first resonance structure, we can see that the cyclopentadienyl anion has 2 double bonds, and so that's at least 2 pairs of pi electrons. But in the second resonance structure, we can see that the lone pair from the first resonance structure was used to create a new pi bond, and that means that those electrons are also pi electrons. In a delocalized system, if an electron pair is ever involved in a pi bond, then those electrons are pi electrons. And since the lone pair in the cyclopentadienyl anion is a pi electron pair, that means that the cyclopentadienyl anion has 3 pairs of pi electrons. And 3 is an odd number of pairs, so it follows Huckel's rule. Just be careful not to overgeneralize. Not all lone pair electrons can be counted towards Huckel's rule, and that's because not all lone pairs are involved in resonance. If we look at the next example, we have furan. We can clearly see that furan is cyclic, and that the 4 carbon atoms in the ring are clearly sp2 hybridized. The oxygen atom appears to be sp3 hybridized. But as we saw in the previous example, one of the lone pairs on that oxygen can be used to form a pi bond with an adjacent carbon. And that means that one of those lone pairs is involved in resonance and should be included in the Huckel's rule calculation. The second lone pair on that oxygen is actually in an sp2 orbital and can't be involved in resonance. A good rule of thumb is to count only one electron pair towards Huckel's rule for any given atom, since we can demonstrate that one of those lone pairs can participate in resonance forming a pi bond. The other lone pair on that oxygen cannot be involved in resonance and should not be counted towards Huckel's rule. So furan, with two obvious double bonds, and the additional double bond formed from one of those lone pairs through resonance, actually has three pairs of pi electrons, and 3 is an odd number, so furan follows Huckel's rule and is aromatic. For our last example, we have pyridine, one of my absolute least favorite compounds. Pyridine smells awful and is believed to cause testicular atrophy, hence my rather unaffectionate nickname for it, Stinky Shrinky. We can see that pyridine is a cyclic molecule, and actually rather clearly we can see that all 6 of the atoms in the ring are sp2 hybridized. Again, we'll assume that sp2 hybridization throughout the ring allows the ring to be planar. When counting pi electrons in the ring, we can see that pyridine has 3 double bonds, so it has at least 3 pairs of pi electrons in the ring. But what about that lone pair on nitrogen? Well, if we follow our rule of thumb, we know that only one pair of electrons on an atom can count towards Huckel's rule. And since that nitrogen is involved in a double bond, that's the pair of electrons that we're going to count. And that means that the lone pair cannot be counted. That lone pair actually exists in an sp2 orbital and is not a part of the resonance in the system. That means that pyridine has 3 pairs of pi electrons, and 3 is an odd number, and so it follows Huckel's rule, and that makes pyridine aromatic. So as mentioned previously, benzene is by far the most commonly encountered aromatic system. At first glance, benzene looks like an alkene, a triene actually, and we know that alkenes can undergo electrophilic addition reactions, adding a molecule across a carbon-carbon pi bond. However, benzene does not undergo electrophilic additions, and that's simply because an addition reaction to a benzene ring would disrupt the aromaticity, making the reaction extremely endergonic and therefore highly disfavored. Benzene instead undergoes a mode of reactivity called electrophilic aromatic substitution, or EAS for short. This is a substitution in which one of the hydrogens on the benzene ring is replaced by an electrophilic atom. So here I showed the general mechanism of an EAS reaction, using XY as a generic electrophile. If you take a quick look at the mechanism, you can see that the aromaticity is actually temporarily disrupted. The temporary loss of aromaticity means that EAS reactions require very strong electrophiles. In the first step, benzene acts as a nucleophile. One of the pi electron pairs attacks the electron deficient portion of the electrophile, creating a new sigma bond to that atom and forming a resonance stabilized carbocation. In the second step, a weak base removes a proton from the same carbon atom that is now bonded to the electrophile, pushing electrons towards an adjacent carbocation, creating a new pi bond, and re-establishing aromaticity. So next, we're going to explore the 5 most common EAS reactions, starting off with halogenation. The EAS halogenation substitutes a hydrogen on the benzene ring for a halogen, typically chlorine or bromine. As you can see in the example, the reaction requires a molecule of dihalide and a Lewis acid catalyst, typically iron bromide or iron chloride. As you'll see, all of these EAS reactions begin with the formation of a powerful electrophile prior to the actual EAS reaction. If we look at the reaction mechanism, we can see that the first step is a Lewis acid base reaction between the bromine and the iron bromide catalyst. This serves to make the Br2, which is already electrophilic, even more electrophilic in character. The adduct formed in this first step then acts as the electrophile in the true EAS mechanism. A pi electron pair on benzene acts as a nucleophile and attacks the outermost bromine of the electrophile, forcing the cleavage of the bromine-bromine bond. The resulting resonance-stabilized carbocation is then deprotonated by a weak base to complete the mechanism. Up next, we have the EAS nitration, which substitutes a hydrogen for a nitro group on a benzene ring. As you can see from the example, the reagents are simply nitric acid and sulfuric acid. Once again, the first part of the reaction mechanism is the formation of a powerful electrophile from the nitric and sulfuric acids. In the first step, nitric acid acts as a base and is protonated by sulfuric acid. The resulting intermediate then loses a molecule of water to form a nitronium ion, which will serve as the electrophile in the EAS reaction. In the EAS portion of the mechanism, benzene acts as a nucleophile and attacks the nitronium ion, breaking one of the nitrogen-oxygen pi bonds. A A weak base then removes a proton from the carbon that bears the nitro group, forming a pi bond and re-establishing aromaticity. Next, we have EAS sulfonation, which is the substitution of a hydrogen for a sulfonic acid group, or SO3H. You can see from the example that the conditions are very simple, requiring only concentrated sulfuric acid and heat. As before, the mechanism starts with the formation of a powerful electrophile and is nearly identical to the nitration. The first step is an acid-base reaction, in which one molecule of sulfuric acid acts as a base and another molecule of sulfuric acid acts as an acid. The resulting intermediate expels a molecule of water to form a sulfonium ion, which will serve as the electrophile in the EAS portion of the reaction, which begins with a nucleophilic attack of benzene onto the sulfonium ion to form a resonance-stabilized carbocation. Once again, a weak base removes a hydrogen from the carbon attached to the sulfonic acid group, forming a pi bond and re-establishing aromaticity. The next EAS reaction is the Friedel-Crafts Acylation, which substitutes a hydrogen atom on a benzene ring with an alkyl group. As you can see from the example, the reaction requires an alkyl halide and a Lewis acid catalyst such as aluminum chloride. One hydrogen on the benzene ring is replaced with the alkyl group attached to the halogen. Once again, the reaction mechanism starts with the formation of a powerful electrophile. In this case, the alkyl halide acts as a Lewis base, reacting with the Lewis acid aluminum chloride to form an adduct, in a similar reaction to what we saw in the halogenation. This adduct then serves as the electrophile in the EAS reaction. The benzene attacks the carbon attached to the halogen, breaking the carbon-halogen bond, forming a resonance-stabilized carbocation that is then deprotonated to form the final product. The Friedel-Crafts alkylation is an important reaction because it's one of the few that you will learn that actually creates a carbon-carbon bond. The last EAS reaction we'll look at is the Friedel-Crafts acylation, which substitutes a hydrogen on benzene for a carbonyl group, typically forming a ketone. As you can see from the example, the reaction requires an acyl halide and the same aluminum chloride catalyst we saw with the Friedel-Crafts alkylation. A second step involves the addition of water, which simply serves to remove the aluminum from the carbonyl oxygen in the product. If we look at the mechanism, we can see that again, the reaction starts with the formation of a powerful electrophile. In this case, the halogen of the acyl halide acts as a Lewis base and reacts with the aluminum chloride Lewis acid, forming an adduct that will serve as the electrophile in the EAS reaction. Benzene then attacks the carbonyl carbon, displacing the chlorine, again forming a resonance-stabilized carbocation, which is then deprotonated to form the final product. Like the Friedel-Crafts alkylation, the Friedel-Crafts acylation is important because it's one of the few reactions you'll learn that form a carbon-carbon bond. It turns out that there are some alternative conditions for the two Friedel-Crafts reactions. The Friedel-Crafts alkylation can be affected with an alcohol or an alkene under acidic conditions. Both versions of this reaction proceed through a carbocation intermediate. In the reaction using an alcohol, the oxygen is protonated to form water as a leaving group, which then leaves to form a carbocation, which serves as the electrophile in the EAS reaction. In the reaction starting with an alkene, the alkene is protonated directly by the acid, forming a carbocation, which serves as the electrophile in the EAS reaction. The Friedel-Crafts acylation can be affected using an acid anhydride. Because no catalyst is used, the reaction often requires considerable amounts of heat.